Hello, this is a presentation by James Baski, a graduate student of Memorial University and the Faculty of Engineering and Applied Science. I'm here to present on the design of a load frequency controller for a single power system network using a trained artificial neural network, and the simulation will be done in MATLAB and Simulink. Now, during the presentation, I'll touch on the introduction where I would introduce the project. I will then take you through the project objective. I would also touch on the approaches of the load frequency controllers in the system currently. Then we'll go through the methodology used in the project. I'll also touch based on the modeling we used for the load frequency controller. Then we would go through the various results in terms of simulations we did or ran for the project. So basically there were 4 simulations, and in the presentation I'll run you through the simulations. Then I'll conclude the presentation on the findings. The modern power system has become structured and interconnected. This is in order to meet the energy demand of the country or the economy. And by doing so, renewable and other sources of energy are tied into the existing grid. These tie-ins comes with its own challenges, and one of them is the frequency fluctuation due to load variations. And in order to mitigate this challenge of frequency fluctuation, a power system needs to incorporate an appropriate load frequency controller. Into the grid. This has informed our decision to design a load frequency controller to maintain the nominal system frequency and coordinate the interactions of the tie-ins. And by doing so, we have tried to simulate a load frequency controller system, and we have also simulated different scenarios where we use different types of controllers to understand the response or the feedback we would get from these controllers. First, we look at a scenario where there is no controller incorporated in the system. Then we introduced a tuned PID controller to see how that also behaves. And in the third scenario, we incorporated a different architectural arrangement of a tuned PNID. Then finally, we instituted the ANN, that's the artificial neural network controller, to see how that behaves. And with the artificial neural network controller, we had to train the controller using the parameters from the tune PNID to see how that also behaves. Now, The objectives for this project is pretty straightforward. The first is to design a load frequency controller for a single power system network using the artificial neural network technique. And in order to achieve that, we are going to compare our technique, which is the ANN, with that of the PID controller, also a tuned PID controller. Then in an instance where we do not have controller incorporated in the system. So we're going to have 4 scenarios in this project, and that should inform our decision on whether or not the ANN technique is suitable for a power system or a single power system. Of course, we are going to observe the frequency response of these outputs or of this power system when the various techniques are incorporated into the power system. During our research, we realized that there are 2 main approaches to designing the load frequency controller. The first has to do with the use of a classical PID control technique, which basically has 2 types: the tie-in line bias and the flat frequency control. Now, these PID controllers are simple, but the main challenge with them is they are not able to withstand our complex power system, the dynamic nature of our power system. The second technique, which is the intelligent technique, usually has to do with fuzzy logic, artificial neural networks, hybrid fuzzy neural network. That's a hybrid between a fuzzy logic and the ANN. And also we have the genetic algorithm, which are also used in the modern power system today. These are intelligent systems. You don't have to manually tune them to withstand dynamic changes. Automatically when the system changes, they are able to adjust and make sure that they sustain the power system to a nominal system where operation becomes continuous. So for this project, we are looking at using the ANN, and we are sure that the ANN would provide us a promising solution to these load fluctuation issues in our power system. So in terms of methodology, the ANN controller cannot operate on its own. It needs data. So we needed to feed the ANN with the data to train the controller. So in order to do that, we simulated a system using a PID controller. We generated the data from this PNID controller. Then the data which was generated was processed to make sure that we do not have any extreme values that will affect our training. Then the processed data is used in training the ANN in MATLAB Simulink. So basically that's the methodology. So once the training is completed, this custom artificial neural network controller is now incorporated into the system in place of the PID controller. And what we want to do is we want to feed the ANN with this data and change or test the ANN with varying inputs. So when we vary the situation, when we change the load in the system, we want to see how fast this ANN is able to adjust the fluctuation to nominal. And mind you, the system frequency was 60 Hz. So we have a base power generation station, and we've tied in an additional power system. We realized that there was a dip from 60 Hz to about 59 Hz. Now, with all this data collected from the PNID, we fed the ANN controller into the system and collected the data, trained the ANN with this data, and we saw to it that it did what exactly it had been designed to do, and we were successful at this. In terms of system modeling, we have the physical representation up on the left corner, top corner, and this is basically a thermal power plant which is coupled to a turbine. This turbine is then coupled to a generator to create electricity or generate electricity. Now, we were interested in measuring the frequency of the generated power. Hence, we used a frequency sensor. Now, this sensor is coupled to a load frequency controller, and when there is a change, or when the sensor measures a lower frequency, the frequency controller senses it, and it sends a signal to the valve control mechanism to open or close the valve in order to maintain the frequency or the power system's frequency to a nominal. So basically, this sensor is the critical part, is the feedback to our control system, and this feedback tends to open or close the valve. Below, or the bottom left corner, is the control system or control model of the above power system, and this is what we used in modeling our load frequency controller. So this is the base frequency controller, and in our first simulation, or scenario number 1, where there was no controller, we are able to pick out the output, and based on that, we use that as a reference or a benchmark to also simulate other models using different controller architecture. Our base scenario, which is scenario 1, is a power system without any load frequency control. So basically, we have our thermal power system generating at 250 megawatts. Then we incorporated we fed an additional 50 megawatt plant into the system to observe the frequency response. And if you look at the top left corner of this slide, we realize that there was a frequency dip from 60 Hz to 59.5 Hz. Now, this is our base scenario, and we want to see if there's going to be changes in the frequency. So our main focus here is the frequency graph and also the combined turbine output power. Moving away from scenario 1, which happens to be our benchmark scenario. Scenario 2, we incorporated a PID controller, as you can see. Now, this PID controller was tuned over several iterations. So what I basically did was I was changing the proportional, the integral, and the derivative components of the PID controller to to ensure that we get a output response of 60 Hz after the fluctuation. So we after the iterations we were able to tune the PID, and we got a frequency response from the original 59.5 Hz to 60 Hz. But this had to go to several iterations, over 60 to 100 iterations, before we were able to reach this output, this close to perfect output. Now, what it translates into is that if we have a power system and this kind of load frequency controller, anytime there is a feeding or we feed in power into the existing system, we would have to tune the controller manually in order to maintain the frequency to a standard or a nominal frequency. This wasn't a good experience because we had to do a lot of try and error in order to get the frequency to this nominal state. Now, in this scenario, we need to look out for where we position the PID controller, because in the subsequent scenario, we decided to change the position of this PID controller to see how it's going to affect the response, and we got an interesting response from the simulation that was done in scenario 3. So in summary, we used a tuned PID. We had to tune this PID over several iterations in order to get a perfect output response. Then when you look at the total turbine output, we got a 300 megawatt output, which was also, though had a lot of overshoots and oscillations at the beginning within the first 5 seconds, but after 5 seconds we had a consistent power output, and which was good. However, the only issue was that the first few seconds we had a lot of overshoots and oscillations here and there. In the third scenario, where we still use the tuned PNID controller, you realize that we changed the position of the PID controller. So in scenario 3, the controller was in parallel with the feedback gain. However, for this scenario, we connected the PID controller between the SAM and the governor system. And interestingly, we realized that we had a match stable with less overshoot frequency response, and the output frequency was almost close to a 60 Hz, which was interesting. And when we look at both the injected or the power system that was injected into the existing grid, we had a much stable load change. The turbine output was what expected, with very few oscillations and overshoot. We had a very minimal overshoot. So I would prefer a PID 2 over PID 1 because PID controller number 1 had a lot of oscillations and overshoots. But this really helped with the oscillations and overshoots. However, we didn't get a perfect 60 Hz frequency, but the output was acceptable. It was within acceptable range. It was way close to the 60 Hz frequency, which I think is a good output or outcome. Finally, for scenario number 4, that is our preferred or proposed controller, which is the artificial neural network controller. Now, when we gained from the scenario number 3 output, we use scenario 3 as our benchmark to train the ANN. So the data, because we got interesting data from scenario number 3, we use the data from this scenario as the input data to train the ANN, so that we could use that as its data. And when we change the parameters, or when we increase or change the input power system, or when we feed in an external power system, we should get a very good response. But unfortunately, the frequency response we got from the ANN was a bit lower than that of scenario 3. But that, I believe, should be due to the data we used in training the ANN. Nevertheless, the ANN was within the acceptable range. Now, for an ANN controller to be trained, we need to, the regression line should be, or the training output should be 1, should be unity. As at the time we were performing our simulations, we got close to 1, but not exactly 1. And we did several iterations of training. That is about 410 iterations in order to complete the training. Now, below is the training performance, where we did train the ANN to close to 1, but not exactly 1, because we were running a lot of iteration, and the iteration was taking a longer time to complete. But all in all, we would say the output was very good, because after training the AI, we incorporated it in the system, as you can see, and we also included a derivative, an additional derivative, into the system to improve the results. However, we got a result that was less better than which was less better than scenario 3. But then we believe that practically the ANN is the best option, because once we train the ANN for future or samples or future tests, when we vary the load, the ANN should be able to respond quickly. However, for scenario 3, whenever there is a change, it means we will have to retune the PID controller, which is not favorable. So anytime, any day, I think the ANN controller has a better performance, has a good and easier operation mechanism compared to the try and error on the PID controller. Yes. Now, in terms of conclusion, we can conclude that the ANN has a superiority in terms of the adjustment to sudden load. So when there is a sudden load, we are not now going to adjust the PID controller. ANN would automatically do the adjustment. And also, since the training is done on past data or data generated or past data, the performance of the ANN will depend on the quality of data you feed to it or you train the ANN with. So that notwithstanding, if we get a perfect data to train the ANN with, we should expect a perfect response. In terms of the tuned PID controller, yes, we got better performance after several iterations, but practically using the tuned PID controller won't be feasible because when there's a sudden change, we would have to go back and retune the PID controller, which is okay theoretically, but practically it's not okay. Looking at how dynamic our power system is nowadays. Now, in terms of practical and reliable solutions, we see the AN controller can autonomously detect and adapt to system changes, like I've explained earlier, which is a better advantage over the PID controllers, and it maintains the nominal frequency after sudden fluctuation. So you are guaranteed that when there's a sudden change in or sudden fluctuation, the ANN controller is able to maintain the frequency back to its original frequency, if not equal, close to, which is acceptable. Yes. Like we explained earlier, the response from the traditional controllers are, especially scenario one, we didn't get a good response because the dip was significant from 60 Hz to 59.5 Hz, and all other controllers had a better output. So the ANN is preferred, or the artificial or the intelligent controller systems are way preferred over the traditional controllers. Now, in terms of our changing and erratic power systems, would say the ANN controller is crucial for this era, and I believe that since loads are becoming dynamic controllers need to be instituted to make sure that the power system is on that level where we have continuous power supply without system failures. Thank you so much for giving me the listening ears. Thank you.